Hello everybody and welcome back to the biomolecules. So, we have been discussing about the structure and properties of amino acids, peptides and proteins. Most of the biological reactions are, as we know, are catalyzed by enzymes. So, enzymes or proteins are the biomolecules, large biological macromolecules which are composed of amino acids. And as you know that there are around 21 naturally occurring amino acids in nature, and these are the structures. Out of those 21 amino acids, one amino acid, that is selenocysteine, is not a coded amino acid, which means only 20 amino acids are coded by genetic code. There is no genetic code present for selenocysteine, and it is a non-coded amino acid. But selenocysteine is found in many proteins, in many enzymes, but it is not necessarily be present in all organisms. Not all organisms have selenocysteines in their protein structures. So, it is not very common thing. If you look at the structure of the amino acids, it has lot of variation, lot of chemical variations in their structures. For example, you start with glycine. Glycine has one hydrogen here. So, it is basically a CH2 here. For all other cases, this CH2 is CH is replaced by some substitutions, and all of these naturally occurring amino acids have L configurations. Except of course, the glycine. Glycine is achiral. All the other amino acids are chiral amino acids. This amino acid is not chiral or achiral, because it does not have a chiral center. All other amino acids have a chiral center, and all of them have L configurations. Naturally occurring amino acids have L configurations, and we have mentioned that the nomenclature of course came from the glyceraldehyde. If you look, this is the structure of glyceraldehyde, and this has L configurations. Sorry, there is a OH group, and OH group is on the left hand side. So, that is why it is called the levorotatory or L configurations. Similarly, if you look at all the structures of the amino acids, they have a equivalent structure of the glyceraldehyde. In this case, this is COOH. I am writing R for general, here H and amine here, and NH2 is on the left hand side. So, they all have L configurations, which ideally means the S configuration. The chemical nature of the amino acids are very different from each other. There are a lot of variations, as I was saying. So, in this part you can see that there are alkyl substitutions with branched chains. There is a cyclic system in proline, which has a secondary amino acid, and that makes it very rigid. There are functional groups, there are hydroxyl groups here which can be functionalized, thiol group here, there is a sulfide linkage, amide bond here, and there are aromatic rings, aromatic substitutions with the heterocyclic rings as well, and there are the acids and the basic functional side chains, like lysine and arginine have amine side chains. Lysine has amine side chain, arginine has a guanidine moiety as the side chain. They are basic side chains. Aspartic acid, glutamic acid have the acid carboxylic acid groups as the side chains. So, lot of variations which allows you to chemically modify the amino acids in an enormous way. So, the basic structure of the amino acid, if you write the 3 dimensional, you can write it in any other way also. I am writing this way, where you have the R up the plane, H down the plane, and this is the carboxylic acid end, and that is the amine. So, this is the general structure of amino acid, and of course, the reason it is being called amino acid is because it has a amine group and a carboxylic acid group. So, acid group and amine group. Amine is base, carboxylic acid is an acid group, and that makes it to have a different structures that I am coming very shortly. If you write a peptide out of it, then you can see, not writing the all of it, CO and then NH, then this will come down the plane R1, okay, R1, CO, NH, this will go up again R2, and it will go, the end is carboxylic acid and here can be the amine. So, it goes and the peptide is drawn in that fashion. You can draw in many other ways, and you can see that they have a peptide bond, which is basically an amide bond. Now, this peptide bond exists in two different structures. It can have resonating structures. So, if you look at the peptide structures, you see that there are, so this bond has a partial double bond character, and apart from this bond, other bond like this and this, or if you see here, this bond and this bond here, this bond and this bond here, they have pretty much a single bond character. So, ideally, if you look the backbone of the peptide or backbone of the protein structures, there are plenty of single bonds. So, a protein should have been a very flexible structure because of because the free rotation around a single bond is allowed, and you can ideally you can rotate the all the single bonds to any directions, to any angles. So, you should have a very flexible molded structure of a protein, but in reality the structure of protein is not as flexible as you think. There are restrictions in the orientations. The basic reason is there are two basic reasons for it. Number one reason is, of course, if you look here at the peptide structure, then first reason is, of course, the all the single bonds that you look here are not actually the single bond, and there is this peptide bond which has the conjugated character as it is given here. Nitrogen lone pair that makes a resonating structures gives you the double bond character here. That is reason number one. Reason number two is there are two planes. If you look at the structure here, for example, if you see this bond, this is the amide bond which has the double bond character, this is the single bond. So, this makes one plane which is given here. On the other hand, this one, this makes another plane, and if you look at this plane, there is an angle, there is a certain angle between these two planes, and this is known as the dihedral angle, dihedral angle between the two planes. So, if you change the plane, ideally you should be able to change the angle because the free rotation around the single bond is possible. This is the single bond and this is the single bond, and they are named as, this is called phi and this is called psi. So, you should be able to rotate phi and psi too freely, but we will see later on just in a while that if you rotate the molecules, then the atoms, they will sometimes bump into each other, and that makes the free rotation around these single bonds not allowed or restricted. So, all rotations around the single bonds are not allowed, and that was given by a plot called Ramachandran plot. That we will just discuss it in a brief while. So, our second thing is that we have seen for DNA that there is a way to write the DNA structures. We have seen that you start with the 5' end and complete it at the 3' end. Similarly, for peptide there is a way to write. NH2, CO, NH, R3, OH. So, you will see that as you move on the right hand directions, you can still continue here, when you complete the chain, there will be a free carboxylic acid on the right hand side if you write in this direction. On the other hand, there will be one free amine group on the left hand side, and this is the way to write a protein structure or a peptide structures, that from usually from amine terminal to the ends up with a carboxylate terminal, and this is called the N terminal of the protein, and this is known as the C terminal. N terminal for amine terminal, C terminal for carboxylic acid terminal, and this is usually the practice that we use to write or to represent a structure of a protein. So, before going to the whole protein structures, I will come back again to the amino acids. There is a property of amino acids which you already know, that I will just briefly discuss. So, I am not writing the stereochemistry now. R COOH. I mean, this is the structure of an amino acid, and as I have mentioned that it has a basic group which is the amine functional group, it has the acid group, and this is acid. So, when you keep a base as well as an acid together, mix them together, then what do you get? For example, if you mix HCl and sodium hydroxide, then immediately you will get a salt, sodium chloride and water. So, HCl, if you take, that is a strong acid, and sodium hydroxide, that is a strong base, if you mix them together, you will get a sodium chloride as the salt plus water. So, acid and base together cannot coexist, they will form a salt immediately. For amino acids, what will happen? There are organic acids and organic bases. So, there will be proton transfer from the acid to the base. So, this molecule does not exist in this fashion, it mostly exists in this way, NH3 plus and COO minus. This is what is called the zwitterionic form. It is called a zwitterion. If you look at the net charge, of course, the net charge is 0, but it exists in the ionic form. So, this one does not exist much. The free form of the amino acid exists in very less quantity. Most of the concentration of the amino acids will be here in the zwitterionic form, and there is one that is where a property called the isoelectric point is coming. It is a characteristic, not a property, it is a characteristic of an amino acid, that is known as isoelectric point. Usually represented by pi. So, isoelectric point is a kind of an characteristics of an amino acid that is defined as, if you have pi is actually defined as the pH at which the concentration of the zwitterionic form is maximum. So, as you vary the pH of the solution, then of course, the acid group is there, the basic group is there. They can be acidity and basicity, depending on their acidity and basicity, the structures would be changed, the proton transfer phenomena would be changed. So, this is the pH at which the zwitterionic form, that is the net charge 0, is the maximum, will have the maximum concentrations. Now, question is how to calculate the isoelectric point, and it varies actually from amino acid to amino acid. So, if you take for example, the structure of alanine, alanine has a CH3 here, it is a carboxylic acid and amine. So, how do you calculate the isoelectric point, or how would you find out the isoelectric point of an amino acid? I am just taking the example of alanine. So, usually it is done by a titration. You do a titration of the amino acid against a strong base, sodium hydroxide usually. sodium hydroxide or potassium hydroxide can also be used. So, strong base against the amino acid. Then and you start it with a very low pH and then see how it is going, what are the changes that you are having. So, if I now draw the structures of the amino acids starting with the very low pH, then what are the structures that are possible, or what are the equilibriums that are possible, and then how can you find out the pi from there. So, if you start with a very low pH, acidic pH, then all of the functional groups would be, the acid will be acid of course, the base would be protonated because this is dipped in strong acid. So, the initially what you will have, you will have a NH3 plus and COOH in very low pH, and then as you increase the pH, as you titrate against the sodium hydroxide, you are adding sodium hydroxide slowly, then that is raising the pH. Then after a certain pH, what will happen? This is an acid which has a low pK value, pKa value. So, that will be deprotonated first. You will get this negative charge here. This is the acidic group, not easily deprotonated. So, this is known as pKa1. This is the first pKa. Then as you move further on, this is minus, eventually this should be deprotonated also, then NH3 plus and will become NH2. So, this is your pKa2, the second pKa. So, the first pKa is for the carboxylic acid, and the equilibrium is from the free acid to the carboxylate anion. The second pKa is for the deprotonation of the NH3 plus to NH2, the basic. Now, if you look at the values of the pK alanine, so your value of Pi would be the average of the two, because the concentration of Zwitter ion, we are basically calculating the concentration of the Zwitter ion, which is this net charge 0, plus charge minus charge, net charge 0, and this is involved in both the equilibrium, this step as well as this step. So, if you want to calculate the concentration of the Zwitter ion, you have to take the average of both the equilibrium. So, ideally Pi is calculated as pKa1 plus pKa2 divided by 2. So, if I take the example of glycine, I have the data for glycine actually here. Then you can write the same thing, the first one COO minus NH3 plus and then this equilibrium still minus, and this becomes a NH2. Now, this pKa value is around 2.3 and this pKa is around 9.6. So, your Pi would be calculated at 2.3 because this is acid, so low pKi, and this is basic, so pKi is should be above 7, 9.6 in this case, 9.6 divided by 2, or it is coming as 5.95. This is the Pi of glycine, and it is pretty much a characteristics of glycine. Now, things are little bit different when you have other functional groups. So, you have acid and base. So, if you have a functional the side chain as another acid or another base, then how it would look like, how would you would calculate the Pi. So, if we take the example of aspartic acid, aspartic acid is this, there is a CH2COOH carboxylic acid side chain, this is acid of course. So, at very low pH everything would be protonated. So, this would be your first form at very low pH. Now, as you increase the pH, as you add more sodium hydroxide, what will happen? Your acid would deprotonate, but it will go stepwise because the pKa value of this acid and this acid are different, and in fact the pK of this is low. For glycine case, we have seen the pK of this is around 2.3, and you know, so this is a derivative of acetic acid kind of thing. Acetic acid has a pKa value of around 4.7. So, obviously, this would be deprotonated first. Minus NH3 plus. Next is this carboxylate would be deprotonated. This acid would be deprotonated minus NH3 plus, and there would be another equilibrium where everything would be deprotonated. This. So, this is pKa 1, pKa 2, and this is pKa 3. Now, the question is which steps you will consider to calculate the Pi. Ideally, we are trying to calculate the concentration of the zwitterionic form. So, where is the zwitterionic form? Where the charge is 0, net charge is 0. So, here if you calculate the charges, the net charge is here plus 1, this is where it is 0, this has a charge of minus 1, this has a charge of minus 2. So, if you have to calculate the zwitterionic form concentrations, you have to take these two equilibrium where they are involved, pKa 1 and pKa 2. So, your Pi for aspartic acid would be, I am writing ASP, aspartic acid, would be pKa 1 plus pKa 2 divided by 2, just like the earlier. And I have the number probably, this is 1 point, value is 1.88, this value is 3.65, and pKa 3, this value is around 9.68. So, your pKa 1 1.88, pKa 2 is this plus 3.65. So, it is already different than glycine, because glycine case this one was coming into picture, divided by 2. So, the average is around 2.76. This is the Pi of aspartic acid. Of course, it is way different than glycine. Glycine has 5.9, in this case aspartic acid has 2.7, then that is because it has a carboxylic acid as the side chain. If you have, instead of the acidic side chain, if you have a basic side chain, then what will happen? You have I am drawing the structure of lysine. Lysine has 4 CH2 here and then an amine acid NH2. So, again at very low pH everything would be protonated. So, this would stay as NH3 plus, this would be NH3 plus as well. So, the first equilibrium would be deprotonation of the carboxylic acid, 4 CH2 here, NH3 plus, this should be minus, NH3 plus. Second one would be deprotonation of either of these amines. So, it turned out that the pKa of this amine is less. So, this would be protonated, this one would be deprotonated, becomes NH2, and then the side chain amine, this would be deprotonated minus NH2. So, this is your pKa 1, which has the value of around 2.17. pKa 2 has the value of 9.04, this is pKa 2, pKa3, this is around 12.48. Now question is, what will be the Pi? How would, which steps you will consider for the calculation of the Pi? Again you try to find out the zwitterionic form by calculating the charge. So this has a net charge of +1, plus this is plus, so this is +2, +2. Here you have +1, 2 positive, 1 negative. Here you have 1 negative, 1 positive. This is your 0 charge, and in this case you have -1. So your change of the charge is from +1 to -1 via 0. So if you want to, it is a usual practice that if you want to find out the Pi of a amino acid, what you look for is where the charge is changed from a positive to negative via 0, or it can be other way around, negative to positive via 0. So that steps should be considered. So your Pi would be, here is the zwitterionic form, which is, so this equilibrium and this equilibrium should be considered. So it is pKa2 plus pKa3 divided by 2, in this case 9.04 plus 12.48 divided by 2, that is coming as 10.76. So this is the Pi value of lysine. Of course, it is very, again, because it has a basic side chain, so the Pi value is high. So that is how you calculate the zwitterionic structures or the maximum concentration of the zwitterionic forms. So now how do you test a amino acid? How would you identify and the presence, or how would you test the presence of an amino acid or a protein? So this is a classic test that is usually been done to find out whether this is a protein or not. This is called a Nin hydrant test, and probably you have heard that name, and you know this is the same test that is used for fingerprint detection. In crime thriller or programs, you have seen that the people are spraying something, and then they are trying to find out the fingerprint from there. They see certain color, usually it is the violet color or the pink or the purple color that appears when you spray that. And they actually spray the Nin hydrant solution, and that is to figure out whether somebody has a fingertip on it. And fingertip means even our skin has proteins and amino acids. So they, if you press it somewhere, some of the proteins or very trace amount of the protein would be labeled there, and it is a very sensitive test to find out whether the amino acids or proteins are present. So it goes like this. This is the solution of Nin hydrant. This is called Nin hydrant, and here I have shown using the amino acid, not the proteins. If you have a free amino acids, then how the test goes, what is the reaction that happens. So first is, if you have the Nin hydrant here, you have OH, it is a diol, gem diol basically, and then you have amine group, this is R. So first reaction is the lone pair, amine is basic and it has a free lone pair of electrons, it is a nucleophilic. So it is a nucleophilic substitution. This goes, attacks, and one OH would be eliminated. And because the carbonyl groups are there, they drag the electrons, that makes the carbon more electrophilic. So the nucleophilic substitutions of the amine becomes very facile. OH, you have now NH, COOH, and here is your R. Now once again another one, this goes, and another OH elements. So, it is minus 2 molecules of water basically, and that gives you this structure, a double bond. And then you have a carboxylic acid. So, it gets decarboxylated. If you have OH, I will draw it here. This goes, it comes back here. Because again, since you have electron withdrawing carbonyl groups, they have the tendency to withdraw electrons, that makes this electron deficient. So, it can attract electrons, and this carbon can attract electrons. So, you will get this form first with a double bond here, and then it gets resonating structures. This is more stable. So, it will form this compound, and now presence of water will hydrolyze this bond. It is very easy to hydrolyze this bond actually, and if you hydrolyze this, if you get ideally a aldehyde and an amine. So, a free amine would be created here, which is covalently attached to ninhydrin. Now, this molecule again reacts another molecule of ninhydrin the same way, 2 times 2 minus 2 water. So, this goes and you get a double bond here. Now, this has a lot of resonance. It can go here, this all the way to the aromatic rings also, or it can be the other way around. It can stay with the enolate form, and enolate form would be more aromatic in nature. So, it is because of this structure that gives you the color. So, when ninhydrin reacts with amine, finally you get this compound, and this compound is usually deep purple in color, and it is very intense. Therefore, you can use a very trace amount of material, very trace, even a presence of very trace quantity of amino acid will show you some color. This is basically a test for the primary amines. Apart from the amino acids, if you have any other primary amines with a free NH2 group, that will also give you the same taste or the same color. For the amino acids, if you have proline, proline has a secondary structure as you have seen, secondary amine. So, proline will not give the deep purple color, it produces yellow to orange color. And now, for the normal amino acids, if you try to measure, number one, you can visualize the color, that will give you the qualitative taste, or it can give you also the quantitative taste as well. You can determine how much quantity of the amino acids are present there by finding out what is the intensity of the color, how much color you are actually getting, and that means if you measure the absorbance of the ninhydrin solution before the start of the test and after the completion of the test, then you will see a new peak in the UV region is appearing at around 570 nanometer. That depends sometimes on the other water, the stuffs that are surrounded to it. Around 570 nanometer wavelength, it will show you absorption maximum, and if you calculate the quantity of it, then you can find out exactly how much of amino acid was present. So, the ninhydrin test can be a qualitative test as well as a quantitative test for the detection of the amino acids. You can use the same test for proteins also, because the proteins have free amine as side chains, lysine especially, and of course, arginine is also there. Both of them have free amine as the side chains. So, they can react with ninhydrin, can give you the same kind of chemistry, can give you the same color. So, this is one test for the detection of proteins. Second, what people do, biochemists or biologists do, once you isolate a biomolecule, then and you want to know whether it is protein or DNA or other kinds of biomolecules, then you do you can directly measure its UV absorption. So, when you look, this is the lambda value, this is the absorbance, UV absorption, this is UV visible, absorption spectra. If you look at the structure of the amino acids, you have aromatic compounds which can absorb UV light, chromophores basically. Phenylalanine and tyrosine, they absorb a very low region of the UV, basically 200 to 220 in that kind of range, which is not a very good wavelength to verify. So, tryptophan essentially that gives you a intense UV absorption, sometimes histidine also at around 280 nanometer. So, if you measure, you will find, if you measure a protein sample, the absorption of a protein sample or absorbance of a protein sample, you will see that around 280 nanometer you have a lambda max or the absorption maximum, and this is kind of it is not really a signature, but it is kind of a preliminary detection for the proteins once you as a biomolecule if you isolate from a biosources. So, these are the two ways that you use usually for the preliminary identification of proteins. Now, coming to the structure of the proteins. So, I will come to the Ramachandran plot just in a bit time. Protein has this skeleton, as we have been discussing again and again, with the stereochemistry involved in it. Now, this is called the primary structure of the protein, which that means simply the sequence of the protein, and then comes how the primary structure of the protein is involved in forming the secondary structure or the tertiary structure of the protein. So, secondary structure means that if you mold the protein, if you since they have single bonds, if you flex the rotate the single bonds around the protein structures, then what are the orientations that you get and what are the short range interactions that are present within the peptide sequence or within the protein sequence. So, secondary structure ideally is the short range interactions, and that because of the short range interactions, it has mainly two kinds of geometry that is formed. One is called alpha helix or second one is beta sheet structure. So, these are the side chains. Now, if you have, for example, here amine as the functional as the side chain, and here if you have acid as the side chain. So, after certain kind of orientations, this amine, free amine and free carboxylate can come in close proximity, and they can have electrostatic interaction, they can have hydrogen bonding. That is just for an example. So, that will change the structure of the total orientation of the protein, and that will make the alpha helix or the beta sheet structure. So, this is the short range interactions or the local interactions that are present within the protein structure. Tertiary structure is the long range interactions. After you get the secondary structure, the protein can mold itself again through our long range interactions, just like disulfide bonds and all. There are other kinds of interactions, hydrophobic interactions, hydrophilic interactions. So, that hydrophobic interactions would repel each other, hydrophilic interactions will bring them closer. So, that makes the tertiary structure of the protein or the 3D folding structure of the protein. We will discuss one by one. So, secondary structure of protein, this is how it looks like. It can have the alpha helix formation, or this is a collagen structure which shows alpha helix formations. This is a helix that is formed by the arrangement of the amino acids, or if your orientation is zigzag orientation of the basic skeleton, then it cannot form the alpha helix, it cannot turn. So, it does not form the helix. Instead, they can interact with another molecule of the same protein, then again another molecule of the same protein, and it will make a sheet structure that is known as the beta structure. And again the beta structure can be of two types. One is that you have started with N terminal here, this is your C terminal. the other protein can be on the same direction N terminal and C terminal, and then you can see that their backbone, this amine and this carboxylic acid, they are coming within the hydrogen bond distance. These two are coming within the hydrogen bond distance like this. There can be hydrogen bonds between the two strands of the same protein and in the same orientation in terminal to C terminal, and that can form a hydrogen bonds like this. Similarly, another hydrogen bond can be formed in this way, and it will make a flat structure. This is known as beta sheet structure, and they are all parallel. We call them parallel because they are all from N terminal to C terminal, same directions, all proteins, all protein molecules. Or it can be the other way around. One molecule of the protein is N terminal to C terminal, other molecules you just make the other way around. This is the C terminal and this is the N terminal. This is N, this is C, again this is N and this is C. So, it goes this way, this one is anti-parallel, this one is again parallel. So, these two are anti-parallel, these two are anti-parallel, and that makes them this kind of orientations. One of the amino acid is out, cannot form the hydrogen bond, the others are forming the hydrogen bond in this fashion. This one is also not forming. This also makes a flat structure. So, mainly two kinds of secondary structures. So, these are all secondary structures, short range interactions as I was saying, that is due to the orientation of the peptides, how much you can flex the peptide or the protein, and that is where the Ramachandran plot is coming. Ramachandran plot is a way to demonstrate or predict the secondary structure of a protein, which form the protein would assume, whether it will be alpha helix structure or whether it will be beta sheet structure, that you can actually visualize or that you can predict using the Ramachandran plot. So, what it does, it basically calculates two angles, the rotation around the two angles, one is phi, another is psi. So, it is again given here, you have one plane, you have the other plane, the angle between the two plane is called the dihedral angle, and this is a single bond, this is the single bond as I have told. So, it is represented here. If I take this as a measure, then this is a single bond, this is a double bond, again this has some double bond character. So, apart from those two, this bond is a single bond which is termed as phi and the other one is termed as psi. So, it is NHR and it is R, this one is RCO. These two angles, these two are the difference between the two dihedral angles. Now, if you fix the phi and then try to, since this is a single bond, ideally you can rotate it 360 degree, it should be allowed. So, if you rotate this bond, then what will happen, I have drawn a structure in this fashion here. So, this is amine here and this goes, this is R1, this is basically R2 and this is where is your R3, this is this is NH and this is your CO. So, now if you keep this fixed and try to move, rotate this bond, then what will happen, all of what you have on the right hand side would rotate along with it, because they are all connected to this. So, once you rotate this bond, everything that is present in this direction would be rotating, and by changing the rotation you can see here, if you rotate this for example 180 degree, then this CO will come the opposite direction. Similarly, this R3 will come on the opposite direction, and this CO and this NH can come in close proximity. Here you can see this angle is actually known as omega, the peptide angle, and of course, this is fixed at 180 degree, because this is the best to avoid the lone pair or electron repulsions. So, omega angle is almost fixed at 180 degree. You can rotate phi and you can rotate psi. So, you can keep phi fixed and rotate psi, then you can see that this carbonyl will be upside down, will be going up, this NH and this CO would have 0 angle. So, that will of course change the structure of the protein, and that will make also the orientations change of this group and this group very different. In this case they are away from each other. If you rotate it for example 180 degree, then you will see that this and this will come in close proximity, and sometimes if these groups are larger, then they can bump onto each other, and that is not allowed. So, Ramachandran plot actually calculates which rotations are energetically favorable and which rotations are energetically unfavorable, and it makes a plot like this. Since a rotation around a single bond is possible 360 degree, the graph is divided into 360 degree, minus 180. So, phi started with minus 180, ends up with 180, that makes total 360. Similarly, phi starts with minus 180, goes up to plus 180, and then you put the points wherever the rotation is allowed, energetically allowed. So, if you see this is the Ramachandran plot for glycine, which has a H here. So, the least amount of steady crowding is involved in glycine, and therefore, the flexibility should be much more, and that is what you see. Almost all rotations are allowed for glycines, plenty of rotation, most of the rotations are fully allowed for glycines, and you get all the structures. If you make a polypeptide out of glycine, you can see both beta structures as well as alpha. So, this region is known as the alpha helix. This is a right handed alpha helix. Alpha L is the left handed alpha helix, which is this region. This region is ideal for beta sheet structure. So, here it is mentioned. Similarly, if you have a proline, proline has a secondary amino acid which has a locked skeleton, therefore, its flexibility is very less, and that will give you highly restricted structure. This is a general structure, a general plot for the Ramachandran plot. If I take a example of a peptide, the same example I have taken, then you will see these are the allowed regions. All the colored regions are the allowed regions. So, for example, if you have phi and psi, this is phi and this is psi. If you have phi as close to minus 135, which is somewhere here, minus 135. Similarly, phi is also minus 135, plus 135 actually here. Then you will see that they have almost a zigzag orientations. If you rotate the phi angle to minus 135 and psi at plus 135, you can see a kind of zigzag geometry, and zigzag geometry is good for the beta sheet structures. You see here, and that is what you see in this case. Zigzag geometry has a beta sheet structure in these orientations. This is parallel beta sheet, this region is anti-parallel beta sheet. And similarly, if you rotate it to 60 degree, minus 60 for phi, minus 60, minus 90, minus 60 here, minus 60, minus 60 for phi and minus 60 for psi here, minus 60, then it will have mainly the alpha helix structures. If you rotate that direction, you will see your backbone has to turn here. Again turns here, you get another turn. So, your backbone has to turn in this way, and you get the helical conformations will come as right handed helix, and this region will be left handed helix. So, that is how if you change the angle, or if you rotate the angles of psi and if you rotate the angle of phi, then which rotations would be allowed and which rotations would not be allowed is given by a Ramachandran plot. It is a calculation, basically calculation of energy, and that finally gives you what will be the secondary structure of a given protein. Thank you.